Hey guys, welcome back. So today we're going to be talking about different goodness of fit tests where they're not all evenly distributed. So a good example of that is actually with dihybrid cross genetics. So for instance, when we have two traits that are actually linked by the same gene, we get something called the dihybrid cross. And I'm not like an expert in genetics or biology. I think I know a few things, but this is actually kind of cool stuff. So here we have all the possible combinations that we could have between two alleles, I believe, with either dominant or recessive. So there are, out of the 16 that we have here, there's one of them, there's only one combination that would give both recessive traits. There are 9 that would give both dominant traits, and then there are 3 of each that would give one of each, a dominant and a recessive trait. So for example, in this example here, we have rolling a tongue, which is a dominant trait. So most people will be able to roll their tongues. If you can't roll your tongue, that's because it's a recessive trait, but of course that would be much more rare. And then having free earlobes that are not attached is a dominant trait, but having attached earlobes would be a recessive trait. So you can kind of figure out where you would fit in these. Both of these are actually controlled by the same gene, which is kind of cool. This would be an example of when we would have a specific model that we're testing against, like a goodness of fit test, but it's not evenly distributed. We don't expect them to be evenly distributed. Instead, we expect them to follow a certain pattern or a certain model, which would be a 9 to 3 to 3 to 1 ratio. So let's go ahead and take a look at that. So here we have our first example, dihybrid cross of 2 genes. There were 124 students that they collected data on from some stat class, and then they made it into this example, which is kind of cool. So our null hypothesis would be that those 124 students would fit into the 9 to 3 to 3 to 1 ratio or model. So it's distributed by a ratio of 1 to 3 to 3 to 9. That's our extended ratio. The alternative hypothesis would be that they're not distributed by that. Now, since this is linked by genetics, we would expect them, they're probably going to follow the link because that's how this stuff actually works. But it is possible that the students, because of some reason, his students don't follow the normal pattern of what we'd expect from a random sample. Now, this could happen, like for instance, if they weren't actually independent of each other. So for instance, I don't know if this was a homeschool cohort or something like that, and or was a family that was all linked together, like in a family reunion. It's possible that you would see more recessive traits or more dominant traits that would show up than just the general population. So for instance, if I don't know if there are a lot of redheads in your family or something like that. My uncle is redheaded, by the way. Then you might find, a family with a lot of redheads probably going to have more or something like that than you would find in the overall population distribution. So just kind of an example of that. All right, so what would we expect? So 124 and 1 out of 16, which would be for both recessive traits, would be 7.75 would be what we'd expect for both recessive. For one recessive, one dominant would be 3/16 of that value, which would be 23.25, and 9 out of 16 of that would be 69.75. So let's go ahead and fill in our chart here. So we have our expected counts for 12. So this is both of the recessive genes, so that would be what we said earlier, which was 7.75, and then one of each, so not being able to roll in free and rolling in attached would both be the 23.25, and then both dominant traits, we're expecting to see the most of those where people have both dominant traits, of course. Now the sum of all of the expected values is going to be exactly the same as the sum of the frequencies as well, which is kind of cool because that's what we're expecting. It is the average, or what would be the expected distribution of those 124 from how we calculated. Of course, that should add up to 124. Next thing we want to do is go ahead and find the residual, the square residual, the component, and the standard residual. So I'm going to put this all in the calculator. We're going to do this for the goodness of fit test. When we get to the independence and test for homogeneity, we'll actually do that differently. So go to stat, edit. Yeah, I've already got stuff in my list here, so I'm going to go ahead and clear that out. So second plus sign for clear all list. And then go back to stat and edit. So for list 1, put all of my frequencies. So I had 12, 22, 31, and 59. So just double check, make sure I didn't have a typo. And then the expected values, we're going to put those in our second list. Okay, so now that we've got that, for the third list, we're going to define that as list 1 minus list 2. So that's going to give us our residuals. So list 1 minus list 2. Okay, so those are all of our residuals. If we add these together, that's going to add up to 0. So what we have to do for list 4 is we actually have to take our residuals and square them. So let me try this again. So we'll do list 3 and then square it. Okay, so those are going to be our residuals squared, and then the components of those are going to be proportionalized by the expected value. So each of these have different expected values, and so these squared residuals are going to be proportionalized by what their expected value was. So this is kind of cool. So for list 5, we're going to take list 4 divided by list 2. Okay, now these are actually going to be the components that we're going to add together to get the chi-square statistic, but to find the standard residual, we take the square root of the components. So I'm going to go ahead and do that while I'm here. So I'm going to take the square root of list 5. All right, so those are going to be z-scores, which we know how to interpret. So the one that was the most unusual looks like it came from the rolling and attach. So I'm going to go ahead and fill these in real quick. All right, so from the rolling and attached, that was a positive residual, so having that many more than we expected, that does seem to be the one that's most unusual, and that would be on its own if we did a one proportion z-test, that would be a z-score of 1.6. So it's not unusual enough to be more than 2, right? So to be what we would consider statistically significant, but when we take all of this together, it might actually be statistically significant. That's what we'll have to see. So whenever we take the sum of all the components, that gives us our chi-squared statistic. That's kind of like a z-score or a t-score, but to be able to tell what's unusual, we can't just do be more than 2 is unusual, because the parameter, it actually changes by the parameter, whatever our family of model is for the chi-squared statistic. So as we increase more and more degrees of freedom, then that's going to increase what value we have to be statistically significant. So what we do to find the p-value for that, we go to the CDF for the chi-squared. So second variables towards the bottom, we have the chi-squared CDF, which would be the cumulative density function. We're going to take our lower value is going to be 6.638, which is our chi-squared statistic. We'll go up to positive infinity. How many degrees of freedom we have? Well, if we have 4 of these all together, so this is a goodness of fit model, so it would be 3. So the degrees of freedom would be 3. So as soon as I know what 3 of these are from the last one, I can figure out how many we have all together. Anyway, then we hit paste, and that's going to give us a p-value of basically 8.4. So depending on what we selected our alpha level to be, we probably would have defaulted to 5. I suppose that's why we always check, so we don't cherry pick. But anyway, this could be rejected, or it could be accepted, or not accepted, but failed to reject a null hypothesis, depending on whether or not we have, depending on the alpha level that we select. Okay, so if we select a 5% alpha level, then we would have failed to reject because it was higher than our 5%. So let's go ahead and go through our assumptions and conditions for the chi-squared. We should have probably done this sooner, but whatever. Anyway, so counted data condition. So we do have counts of the number of students that had each one of the these phenotypes. The independence assumption, each student should be independent of the next student as long as they are like genetically independent, meaning they're not related to each other. So if this is a homeschool cohort, you're probably going to violate that, right? If this is unless we had twins, that would probably be something. If this is like a senior stat class, most of the time I don't have siblings in there, but I actually have had twins before that could have caused that issue. So each student's genetic traits should be independent as long as they aren't related to each other, like literally related. All right, if I want to generalize this to the overall population, which I'm really not interested in, I'm just trying to see if my students specifically fit what we would expect for the overall. So this might not even be necessary because I'm not generalizing across to all stat students to a larger population. So anyway, randomization, this is not a random sample, but it should be representative of what's going on. Maybe it depends. Then 10% condition, this is less than 10% of all students. So if I did want to generalize to a larger population of all stat students, then you probably could. Expected cell, were we expecting at least 5? Well, our smallest one that we were expecting was 7.75. So yes, we were expecting at least 5 counts in all. So we had a large enough sample to be able to use the chi-squared model. All right, so the degrees of freedom that we had was 3, so our model looks like this. Notice that the mean would be the degrees of freedom, 2 less than that would be the mode, which is 1. So our chi-squared statistic we said was 6.64, which if we calculate the p-value, which we did from the normal CDF, gave us about that 8%. So that's where we got the 8.4% here, which would not be statistically significant. All right, so example 2, the chi-square test for homogeneity. So this is going to be, the test for homogeneity is whenever we are comparing from two different samples, one variable from two different samples, or even multiple samples. So to test to see if they are all, if this group is homogeneous, meaning that it's like evenly distributed across all of the different samples or all the different groups that we're getting. So a test for independence is one sample with two variables, like for instance survival and class with the Titanic. That's a test for independence. Test for homogeneity is done the exact same way, except now we're testing one variable across multiple different samples. So that's a slight subtle difference between the two, but there is a difference nonetheless. The calculations and how we do it is the same though. So this is a good example for a test of homogeneity. In 2006, a survey of graduates from 4 different colleges of an upstate New York university. So there are several colleges, like for instance, I graduated from the College of I believe, Math and Computer Science at UCO. So that was its own separate college. Or the College of Education, you have the College of Liberal Arts, etc. So the same university has multiple colleges that are all like separate departments, I suppose you would say, within that university. So just maybe you're not used to that. They were asked if they were, they were asked if they were already employed or going to seek employment after they graduated, or if they were planning on continuing their studies in grad school, or if they were going to take time off, volunteer, travel, or do some other activities after they graduated. The data appears in the following table below. Okay, so basically from 4 different colleges from the same university, the people who go into these different things, what are they planning to do after they graduate? Are they planning to do grad study, or seek employment, or do something else, like join the Peace Corps, or travel, volunteer, something like that. All right, so write your hypothesis. So our null hypothesis is that it's going to be homogeneous, meaning their choices of what they're going to do after they graduate does not depend or is independent of what their college, or what basically kind of what field of study they were involved in, will be a good way of thinking of that. So that would be our null hypothesis. So all students from different colleges of the same university have the same postgraduate plans, meaning there's no association between them, or that they're homogeneous. It doesn't matter what, in other words, it doesn't matter what college you were part of, they're all planning on doing the same thing, so it's homogeneous. So the alternative would be that the students have different plans depending on what college they're in. So in other words, there is an association between them and they're not homogeneous. It really depends on what college you're a part of to decide what your plans are after you graduate. So here's the two-way table that we have here. So each one of these, think of them as a separate sample. So we had a sample of students from Ag, we had a sample of students from Arts and Sciences, the College of Engineering, and then we have the College of Social Science. So think psychology and sociology as well. So like how people behave in society and stuff like that. So anyway, here's the totals that we had for all those samples, and then the total totals over here, which would be our marginal. All right, so if I graph these out, the relative frequencies for each one of these colleges, we can see those. So here are the 4 colleges, like our 4 individual samples, and then here's the distribution for those that are seeking employment, going to continue their studies in grad school, or going to do something else. So the one that looks like they're going to do something else, most probably not surprised, would be social sciences. Engineering is pretty focused on either continuing the studies or seeking employment. They're not going to go join the Peace Corps, as you might imagine. Agriculture and social science, you can see what's going on there. Most of those in agriculture are not going on to grad school, surprise, surprise, and they're just going to go straight into seeking employment. So these do not look the same, especially engineering here sticks out and agriculture here sticks out. So those are the two to me that stick out just from the graphic. So let's go ahead and compare and see if we have enough evidence to say that they're not homogeneous depending on what college you're involved in. In other words, saying that it actually depends on what you're doing. They're not the same. They're heterogeneous instead of homogeneous. There you go. All right, so let's put this in the calculator. Let me go back to the actual data and let me show you how you do this. This would be a mess to try to put these all in one list. And this is really where we're going to have to use matrices. And that's how it's done anyway. So let's go to second inverse, which is the matrix. I'm going to go to edit, and I'm going to do 3 rows by 4 columns. So it's a 3 by 4, and then I'm going to put in all this data. I'm probably going to cut so that we can save some time. Okay, so briefly look over it, see if you have any obvious errors or anything that's missing. Usually it's a decimal for me, so all these are only 2 decimals, so we're good. Or 2 place values. Okay, so that was matrix A. So I'm going to go ahead and run a stat, a test, a chi-squared, not a goodness of fit test, because I'm not testing it against a specific model, which I believe you can do with matrices. Or do you have to do lists? I'm not sure. Usually goodness of fit is with a single variable, so it's all in the list. Anyway, so we'll do a chi-square test. Again, it doesn't matter if it's a test for homogeneity or if it's a test for independence. Again, whether that's multiple samples with one variable or two variables with one sample, it doesn't really matter. So our observations are going to be in matrix A. We're going to export the expected values for matrix B if they're actually truly independent or if they're homogeneous populations or different groups and from different populations. Then we'll calculate. So our chi-squared statistic was a sum of the components of the chi-squared of 54.5. Our p-value, which is nice that they give that to you as well because they've already calculated the degrees of freedom of 6. By the way, that would be 1 less than number of rows, which is 2, times 1 less than number of columns, which is 4. So that would be 3 times 2, which is 6. That's how they get that. So as soon as I know 1, 2, 3, 4, 5, 6, I can fill in all the rest of these if I know the marginal total. So that's how you find the degrees of freedom, by the way. All right, so the p-value is basically 5.8 with 9 zeros in front of it, so 0.000009 times 5.8, which is less than any reasonable alpha level. So clearly we have enough evidence to reject the null in favor of the alternative, which, as we might suspect, that the colleges are not homogeneous, that the choice that the students have on what they're going to do after they graduate actually does depend on what college they're a part of. So they're heterogeneous instead of homogeneous, meaning we believe that there's a difference between each college. Okay, so we can graph that out here, which I have. So our chi-squared statistic, a p-value less than 0.0001. Oftentimes in stats, which is what we call statistical zero, if we have anything that's less than 0.01 of a percentage, we just say that's practically zero or statistically zero, and we don't even bother to write all the precision because that's not necessary. So that doesn't even show up. 54, the highest that our graph even kind of shows up is a 18, so way beyond that, way off the chart. So basically it's a statistical zero. Calculate p-value from the sum of the components. We did that here. State your conclusion. So the p-value is based on the probability if they really were homogeneous, meaning each college had the same basic outcomes. Then the probability of observing the differences that we observed is basically statistical zero, meaning we have enough evidence to reject the null hypothesis for any reasonable alpha level, stating we have overwhelming statistical evidence to suggest that they are not homogeneous. In fact, the different colleges are heterogeneous, meaning they have their own specific set of plans afterwards. So they're not all going to do the same thing at the same rates. All right, examine the table for standardized residuals to the right or below here. What two values impacted our results the most? So we're looking for our overall absolute value being the largest magnitude. So that would be grad school. There was a deficit of people from ag that were going into grad school. So there's obviously not a lot of people who are getting an undergrad in agricultural college that are going on to grad school for ag. So that was our largest deficit, or the second largest. The first largest was engineering college that were going to do something besides grad school or employment, whether that would be volunteer work. I actually know some guys who did engineering, and they did kind of like mission work with engineering, and they would go to other countries that really needed a lot of help, usually working with providing clean water or improving infrastructure, and they would basically work for free. There's also a lot of people in the medical field that do stuff like that. I forget the specific name for the program that they were involved in, but it's actually kind of cool. So there are people that do that, but that is a vast minority of what we would expect from people who are from the College of Engineering. They're usually going straight to employment to pay off those student loans, it makes sense, or they're going to grad school. There was also the highest above the one that was the third from there would be engineers going into grad school, more than what was expected from those who were going to social sciences, agriculture, or the arts and sciences, I believe. Okay, example 3, chi-square test for independence. So an example of that, so this is going to be a 1991 study from a hospital in Texas. Took 626 patients with an unrelated disease and tested them for Hep C and asked if they had any tattoos and if they got them at a tattoo parlor, if they did have tattoos, or was it done at home or something like that, or prison tat. I don't know. Is that's probably what's going on. Let's just be up. Anyway, lurking variables there. So the count of their responses are displayed in the contingency table below. So whether or not they had C, yes or no, and where they got it, or if where they got their tattoos, if they had tattoos or not at all. So this is one sample, okay, across two variables. And so just like Titanic, we're sorting from one sample across two variables. So this is a test for independence, not homogeneity between one variable across multiple samples, like different colleges samples, but this is a test for independence. Very similar, done almost the same way, done with matrices, but as a test for independence instead of for homogeneity. All right, so here we have a graphic here of whether or not the proportion that were infected did not have a tattoo, had a tattoo from a tattoo parlor, or it got tattoos from somewhere else. So obviously it does not look like they're evenly distributed, so it looks like just visually we have evidence of an association. And we would call an association instead of heterogeneous populations. Anyway, moving on. Okay, so let's put this in the calculator and just do it, and then we'll go back and look at our assumptions, which we should do first, but I don't care. Okay, so let's go to second matrix, go over to edit. We're going to do a 3 rows by 2 columns, so 3 by 2. Okay, and then I'm going to put in my data. So I've got my counts here. I don't see any obvious any issues there. So let's go ahead and run a stat test. We're going to do a chi² test. This is a test for independence, not a goodness of fit. We don't have a specific model like or anything that we're going off of there. So let's go ahead and hit calculate. All right, so it looks like we have a very high chi². But we also can't really, we have to interpret the chi² model based on the degrees of freedom. So if we had 57 degrees of freedom, then this would be a very typical chi² statistic. Okay, so it changes based on the parameter of our degrees of freedom. But in this case, our degrees of freedom is just 2. So as soon as I know 2 of these cells, I can fill in all the rest of them here. Okay, so anyway, that means our mean is going to be at 2. The mode is going to be at 0 actually. So this is going to be, look like an inverse model essentially whenever I show you that slide. Okay, so 2 degrees of freedom, they already calculated it for you, which is fine. Our p-value is essentially statistical 0. All right, so let's write our hypothesis. So the null hypothesis is that they're going to be independent, basically that tattoos and where you got them are independent of hepatitis C. Okay, and then the alternative is that there's an association between having a tattoo or where you got it, and in other words, saying that they're not independent with hepatitis C. All right, so our distribution again looks like the inverse because the mode is actually 0. Our mean, the balancing point, is at 2. Our degrees of freedom, we already said the chi² statistic was 58, which is going to be way off the charts, meaning we're going to have a very, very small p-value of basically statistical 0. All right, state our conclusion. With such a low p-value, it's lower than any reasonable alpha level. We'd have overwhelming evidence, statistically significant evidence to reject the null hypothesis in favor of the alternative, saying that there is an association between tattoos and where you got them and hepatitis C. Yeah, say all that fast. Moving on. Standardized residuals. So they went ahead and gave that to us. What's kind of nice is that whenever we run a test, if we go back to the matrices, and if I want to, let me try that again. If we go back to the matrices and I click edit, they export the B1 is going to be our expected values. So is there a way to take the expected values, subtract matrix A from matrix B, and then eventually find the standards? I think there's a way to do it, but it's really nasty. So they give it to you from the calculator. Okay, so you won't be asked to do anything like that. It is a lot easier to go through all of those steps if we have them down in one list, like what we do with a goodness of fit model, because it's usually one variable. All right, so here we go. Which one was the most what two impacted? Okay, so a vast overrepresentation of 6.6 standard deviations of those who had tattoos from a parlor that had hepatitis C. Oh my goodness, that is very suspicious. And the second most would be a vast underrepresentation of those who did not have tattoos that had hepatitis C. So there were far less than we would have expected among those who did not have tattoos that had hepatitis C. So it looks to me like there's a strong association between, at this point, even just having a tattoo and having hep C. So that's interesting. we'll take that with a grain of salt, and we'll continue on because the plot thickens a little bit. So calculate the expected counts for patients who have tattoos and hepatitis C. Are they larger than 5? So remember, we didn't do our association. You didn't check our assumptions and conditions, and we might have violated something. So if they're independent, then the probability of having a tattoo times the probability of having hepatitis C, the probability of having both, it should be the overlap of those two. We just multiply them. So if I take 52 out of 626 times 47 out of 626, or 6, that would give me the overall probability. Then if I multiply that by my total again, that'll give me the actual count. So what I did is I just didn't divide it by the total twice. Okay, so anyway, whenever we put that in the calculator, we get an expected amount of 3.904. And if I look in the calculator, that's at 3.904. So we can actually check the expected values. They do them all for you, which is lovely, by 3.904. So all these should be above 5. In fact, that one's not above 5 either. So having hepatitis C with a tattoo and having hep C from a parlor or without a parlor, both of those lower than what we expected. So we violated that condition. It was too small of a sample, meaning these small amounts could actually heavily skew these two, and that's maybe why we had such a high z-score here. So what we need to do is we actually need to go back and gather more data from maybe from another year, or wait till the next year, or go to another hospital and ask them whether or not they have hep C from their blood test, obviously, and then whether or not they had tattoos and where they got them. So another way that we can do this, so example 4, is we can actually combine whether or not they got a tattoo from a parlor or anywhere else, and combine those into one. So we basically added those two together, basically collapsing it to like a marginal distribution of whether or not they had a tattoo or not have a tattoo. Okay, so now let's check and see if we violated the condition. So 113 times 47 divided by that gives us a total. Okay, now everything's good. We have a large enough sample that we can actually run this. So let's rerun the test. So I'm going to go in here and edit matrix CA. Okay, so here's, now it's actually a 2 by 2. So we have 2 rows and 2 columns. So 25, 88, 22, and 491. Alrighty, looks good. Let's run the test for that one. So that's going to be a chi² test for independence. This is all good to go. Hit calculate. We still have a statistically significant value. Our chi² is a lot lower than it was before, but we also have fewer degrees of freedom than we had before. So that kind of changes our model as well. So our p-value is still lower. It's a statistical 0. It's lower than any reasonable alpha level. We'd still be able to say there's a strong evidence for an association between having a tattoo and having hepatitis C. Okay, so we did our p-value, we stated our conclusion, good to go. Causation, that's where it comes down to. So there are oftentimes that we see things that are unusual, it looks like there's an evidence of an association, or when we take it all holistically, it looks like there's something going on. The book actually has many examples of these things that probably would make you boil your blood, actually. So look at those examples, by the way. But oftentimes we need to remind ourselves that correlation is not equal to causation. So it doesn't mean that if you get a tattoo that you'll get hepatitis C. There could be some things that are going on here, some lurking variables, right? We can't actually make causal relationships, conclusive causal relationships, until we have a carefully designed experiment where we randomly assign people to get tattoos or not to get tattoos, and then we see whether or not they develop hepatitis C. That would be pretty obvious, right? So they start out without it, and then they get a tattoo and they get it, then we know where it's coming from, right? Okay, so there could be other underlining variables that are going on with people that have tattoos that might be other things that might be putting them at higher risk of contracting hepatitis C. So what do we think those things might possibly be? Good question. So how can you catch hep C? So it's through bloodborne pathogens. So your blood has to come in contact with somebody else's blood who is infected with the virus. So the number one way that hepatitis C is spread is through the sharing of needles, syringes, and other equipment for intravenous drugs. So there you go. So one of the reasons, and this could just be one possible lurking variable, is that people with tattoos apparently might be more likely to be sharing needles. Okay, not just needles for drugs, but also, I don't know, maybe the needle from the tattoo. So it is possible. Now, if you're going to an actual tattoo parlor to get it, but even we saw there was most of them actually came from tattoo parlors, if you want to go back further. they should be sanitizing the needles between tattoos. But if they don't, they think, it's not a big deal. We'll just take the blood from this person, share it with the person from this person that does the tattoo afterwards. Okay, that's obviously bad practice. There are other ways that you can read here, just in case you're curious, and ways that you cannot get Hep C. This is also very similar to AIDS or HIV as well, in case you're curious, because they're both spread through bloodborne pathogens. So let's think of it. Somebody who, that's kind of interesting, somebody who has tattoos, not only are they probably more likely, or they could potentially be more likely to be involved in intravenous drugs, and then obviously the fact that they are sharing needles potentially with getting tattoos with other people who get tattoos. Also, this is kind of ironic that they just so happen to have tattoos. This guy doesn't, I don't know who he is, but I know this guy. Conor McGregor does have tattoos, and he's also involved in MMA. So maybe it's the fact that, which is also obviously a very bloody sport, just like boxing or rugby or anything else like that, where they have a lot of open wounds, or I suppose hockey maybe. So potentially that's also what's going on here. What's interesting, in case you're curious, you're still here in the video, so I suppose you are curious at this point, is that they do not allow players in the MMA. They're not sanctioned to fight or licensed to fight if they have any sort of bloodborne diseases or illnesses that could be passed on. So they're not allowed to fight. Same thing with boxing, I believe with rugby as well. So they test them, they do blood tests to make sure that they don't have Hep C or AIDS or any other bloodborne diseases that could be spread through blood, obviously. And if they do, they're not allowed to fight. So think about it. Kind of cool stuff. Hope you guys enjoy this. Lot of fun things. So I didn't make the video from the previous assignment because it was kind of homework, and this one should really help you guys out with that. So I'll see you guys later. I hope you have a good day.